Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
And I'm Philip Sage with the Manaway Group in Australia.
Hey, Philip. We got a question the other day. I mentioned it as we were talking on the last one, but I thought I wasn't sure who I wanted to bring it up with. And at the end of our last episode, it was like, oh, Philip, we need to talk about this. So it went in summary. The question was, the title of the summary was, what's the difference between the quality type statistics and the reliability type statistics? And the underlying question was, I'm in college, and I have the option to take a quality statistics class, focus class, or a reliability statistics class. And my short answer to him is take both. As a reliability engineer, you need to know both. If you're going to be strictly a quality engineer, but you actually want to do a good job and make a difference with your company, take the reliability statistics. It was kind of my short answer to him. And it wasn't clear whether it was in either or. Yet the underlying question was, what's the difference? There's going to be some overlap, and I think they saw that in the syllabuses. And so wanted to know why are they separated? So I thought, you've been dealing with statistics a lot and dealing with reliability a lot. And in our last episode, we were talking about extrapolation a little bit, and that's what sparked my thought that, we need to talk about this one.
Yeah, I think your recommendation is probably accurate, but we can expand on that because they are different animals, but they are absolutely intertwined and related and important for a reliability professional to know and to be able to work in those areas, because some of the biggest quality improvements don't come from quality engineers. They come from reliability engineers working on the machine. I'm going to show my age a little bit, but my training goes back in statistical process control, back before there was such a thing as a Six Sigma program. And
before Motorola did their stuff? Motorola. Oh, man.
It's trained in a process called integrated process control, which was helped drive the Sumitomo Metal Company in Japan, which was heavily influenced by Deming and others. And the interesting part of that whole quality arena, if you will, it's quality, like reliability, has legs and like a bowl of spaghetti, it goes everywhere.
Yep.
If we stereotypical generalize quality, then we would say that perhaps we might suggest that quality seems to be dealing with the normal or Gaussian or bell-shaped curve, and there's I think a reason why that there is that focus. But and the reliability, while we look at a variety of different probability distributions, we are often in the Weibull or perhaps log normal distribution, because that matches the failure data. And when we model anything, I just make a broad statement that the model is only valuable if and only if it represents the real world. So that, because the real world's different in reliability from perhaps the process quality demands, there are different distributions.
Well, it's part of it is, and I think there's all kinds of variations. I mean, you mentioned Six Sigma and this, reducing variation process is. I'm sure you remember there was this two car companies were building the exact same vehicle or engine. I think it was engine block. And one was in Japan, one in the U.S. And the U.S. ones had all these problems in the field, all these blocks or transmissions or whatever the device was, had a horrible field failure problems. Whereas the Japanese made ones in the same vehicle, sold in the same countries, were great. They didn't have hardly any problems, and they dug into the depths of it. And I think the gist of it is that the U.S. guys said, well, it's in spec, ship it. Where the Japanese said, well, it's not perfect yet, improve it. And they continued to do continuous it's probably a bad choice of phrase there, but it continued to continuously improve. And so each of those devices were well within spec, which kind of reminds me of the old Motorola type Six Sigma type stuff. Is you improve your process or improve your design so that the chance of it going out of spec is remote. Whereas the U.S. car manufacturer at that time was, it's our gauge says it's a millimeter in, so it's good, ship it. And lo and behold, it's measurement errors not being taken into account to the extra wear or the lack of fit or the lack of seal or whatever it was adds up, and it tends to wear out faster or cause problems faster. I look at the quality reliability in that spectrum where we have a specification of a minimum or a maximum or a range, and we use all these tools to measure the variability, the location and the variability of the shape and scale of it. Whereas reliability, we tend to start at time zero, wherever we kind of decide to measure zero at. It's arbitrary sometimes, which leads to other problems. Yet we're dealing with the variability of time to failure more often. And it's although I've seen it, and I was in a legal case, and somebody showed me a data set where they had a very large 3-parameter Weibull distribution where the failure-free period went to before the products were created. That kind of violates all kinds of problems. It doesn't matter what kind of statistics you're doing. But it's a true statement. It didn't have any chance of failing when it hadn't been built yet, created yet.
Yeah. Yeah, there are challenges with every data set, and probably in that case, the Weibull 3-parameter Weibull model was probably not a suitable model choice.
Probably.
Yeah.
Really? Probably.
Yeah. I think back to the topic, of should we study quality in college, or should we study reliability topics? And I think your answer was actually very good. We should study both. And you're right. Reliability engineers are obsessed with failure, if you will, and they unfortunately don't spend enough time thinking about what constitutes failure.
Yeah.
And as a result, they miss. And most, I always laugh when if the HR people, if anybody's listening, please forgive me for saying this, but when I look at one of your position descriptions, I realize how shallow the understanding in the organization is of what a reliability engineer should be doing.
Mm-hmm.
And the comment I made earlier is that the reliability engineer is uniquely poised to solve a great number of quality problems if they begin to work on those quality problems. And it doesn't matter whether you've got a TQM or a total TPM or an operational excellence or a lean methodology deployed at the factory. One fundamental thing is that you can't change the machine by changing the way the people operate the machine, act.
Well, isn't that one of Deming's main points? Is you actually have to change the process. You can yell at your employees all day long, but until that machine fundamentally changes or your process itself or the materials you're using, unless you make a fundamental change, you can. And you know what I'm talking about, the red bead experiment, where he has the CEO up there on stage and he's has a little paddle and he's scooping out beads, and if you have a red bead, you failed, do it better. And they're just random in this bucket.
Yeah. No, I think the challenge is that with reliability engineers, we often gravitate to the machine broke down, it ain't moving. And that's what we consider to be a failure. Whereas in reality, many machines I've worked on through the years are failing to make first pass quality because something's wrong with the machine. Yeah. Yet it's running.
But if you and I are using a cell phone, just because it turns on, if it can't make a phone call, it's failed. Just because I can text instead or I can send an email doesn't mean that it's working. And I have that argument with, well, you have a backup. It's redundant. Isn't that reliable? Like, no. I think, going back to what you're getting at, I think, is what we, I'm using big we here with reliability peers, is we bring a sense for what's the failure and what's its consequence. So if a label's not aligning on a bottle, for example, the labeler is running, it's putting labels on, right? But we have to rework it, or it gets scrapped, depending on the product you're working with. And if that costs you money, it's a failure. And the quality guys are out there pulling gauges out and saying, well, it's only off by 2 millimeters. That's not a problem, is it? What's our spec on this? You're kind of missing the point here, guys.
The process I was involved with was kind of looked at the statistical process control and the quality arena a little bit differently. It treated each process as a black box. Mm-hmm. And the theory was, if I control the input variables, if I can identify all the input variables and control those, then I should have good control over the output variables because the process is a black box. Where that over the time I found that fails is that the process itself has its own source of variation. Yeah. And at times we had KIVs, or key input variables, that were all perfectly in control and great CPKs within the specification limits, yet our KOVs, key output variables, a few of those were not in spec. And so we began to ask the question over time, why is the process varying? And it led us down the path to how do we do better maintenance and improve the overall precision that the way that the machine operates, mm-hmm. so that it doesn't induce this extra variability that we don't have coming into the machine, because we're tracking that.
Yeah, I learned that the hard way. Is that I started my career in industry as a shift supervisor in a factory, and then later a manufacturing engineer, and I'm dealing with a prototype, and we were trying to get it through the plant overnight so that the engineers could have their prototypes in the morning, kind of thing. And we could do that. Our capacity was such that we could do it. And the actual duration of making our products wasn't all that high, but you had to change settings. It cost us a bit of time, but we would get it through the system, these small batches. And I do that overnight. And then the next time I come on the plant floor, this engineer's yelling at me because the products doesn't work. And they're like, well, you designed it. You got to realize that the only thing we can do in manufacturing and follow your instructions is make it worse. We can't make it better. And he looked at me like, I never thought of it that way. So he thought we could hold these tolerances that he didn't tell us about. He says, settings here and settings there. And we just ran it like we ran any other product. And the equipment, different temperatures, different heating, different cooling systems, all the different stuff that affect its actual performance, we're within our expected normal range of variation. Yet he arbitrarily said, no, that needs to be 100th of what it is in reality. And I'm like, well, that ain't going to happen unless you can help us redesign this equipment to be capable of doing that. And he looked at me like I was from outer space. And I said, do you realize we can't make your design better than it is? We can make it worse. That's the only thing we can do. We can make it consistent, which is an improvement. We can make it consistently worse, which is, getting better. And he walked away at that point. He came back a week later with a different recipe.
Yeah. And when we focus on the difference between quality engineering and reliability engineering, I think you're focused on the disciplines that look at from the statistics at the distributions, and in quality engineering or quality control, we're very focused on the normal distribution, and we often average the data readings or observations and that's a fundamental. There's a fundamental reason. If you take a number of samples from any distribution and group them and average them, and then track that, those average values will actually begin to be normally distributed due to the laws of mathematics and the central limit theorem.
Central limit theorem, yeah. And I always thought, and I don't know enough about the history of the development of Six Sigma and process control and all those stuff, but I have to imagine that a good amount of the things we do to make the data more normal, taking advantage of the central limit theorem, was because we could deal with the central limit theorem in the 40s and 50s. Is that the mathematics of anything other than that were really more complicated than we had. We could do it if we had enough time, but if you're making readings on an ongoing basis and you're dealing with 15 different distributions, it was really a pain. It took a lot of work to manually sort out what you're dealing with and is this in control or not in control. So I think Schuhart and the others went to great pains to say, well, let's get it normal enough that we're good enough.
Yeah. And Short, you mentioned Short. I was actually going through my book collection, which you know is extensive, and
Yes.
I found his book, and I've got actually two of Deming's books. And you're right. The key fundamental thing is that the normal distribution allows you to develop a rather easy method that can be taught to the masses and deployed in the factory floor that gives, like an X bar R chart that you're sampling a particular variable to see whether it's in control. You can do that by hand and paper on an ongoing daily basis right on the shop floor, which is where those used to be deployed. Today, there's much more computerization, or those things aren't measured at all.
Well, there's a whole nother topic, yeah. But the idea, I think, one of the, just dawned on me is I don't know of any statistics in the life data analysis type stuff or accelerated life testing, those kinds of things, that uses sum of squares. The ANOVA tables and design of experiments and a whole bunch of other tools have you using these sum of squares. I don't know the history of that stuff at all, but when I go to do life data analysis, I probably come close to it when I'm doing regression analysis, yet I'm using maximum likelihood, and I don't think there's any sum of squares in there.
No, the maximum likelihood, so you're pretty much taking the probability density for the observation, or the probability of the observation, and multiplying them together, and then maximizing the parameters that generate the maximum of the likelihood equation. But you often, you pretty much, because the likelihood equation, you're multiplying things that are less than one together. If you've got 1,000 things less than one, then you're 1,000 decimal places, or a lot of decimal places, before you actually have meaningful data. So the common approach is to take the logarithm of the likelihood function, which is multiplying all those things together, and then you're simply, in very generic generalization terms, you're adding together the results of those equations, and then you apply a maximization algorithm to recover the best parameter estimates. And that method was developed by Fisher, I think, in 1912. And it's been a source of great debate whether it's more accurate than the medium rank regression methods, which take the sum of the square of the residual error between the line of best fit and the data point, and use that to plot or to understand what that slope is and where its intercepts are with critical values.
Then you can deal with it. Yeah. Now, I know I've told you before, but when my regression analysis professor, when I was doing my master's, was Australian, and he, besides having an amazing accent, he actually knew how to teach really, really well. He even had a squirrel show up at the door one day, and if it had a piece of paper, I'm sure it would have been taking notes. It was just fascinated what he was doing on the board. But he said, when it all comes down to it, if you get an 8.5 by 11 sheet of paper and put an XY axis on it and draw your line on it. And if you're using, a normal distribution paper or Weibull paper or whatever, it should be a straight line. If it's a good fit, it's a straight line. And somebody asks, well, how straight does it have to be? He says, well, if it's perfectly straight, you really need to be suspicious about your data. But if you take a number 2 pencil and lay it over the data set, over where the line is, and if it gets most of the points, if you got 10 points and one of them's off that line, it's good. If you got 1,000 points and 100 are off that line, you're good. And he said, if you hold the page kind of up, he's holding this piece of paper, kind of holding it on edge. So he's looking across the plane and goes, if the lines all kind of line up, it's good. And somebody else says, so why are we learning, the software stuff? And he goes, well, that's just to confuse the innocent. That's what his phrase was.
Well, when I still probably 2 years ago, I was doing an example working on one of Wayne Nelson's data sets, life data analysis, and in preparation for a conversation with Wayne. And I came to just the realization that even though we're not using computers back then, we were using computers, just a different form.
Yeah.
And the computer was actually the graph paper itself.
Right.
And the way it was constructed and how the lines were spaced allowed you to plot the data. It was this long in service, and I think it's got this value from the rank or some other method to estimate its unreliability. And when I draw the line, if it's this type of distribution, I should get a good fit on this particular paper.
Yep.
And if not, I need to go into the drawer and find a different type of paper.
That's right.
And try again.
And one of the things that whole process, and this applies with normal distribution or any regression analysis, is just plot the data. What's the histogram look like? What kind of probability density function is a clue? But more importantly is you need to stop with the statistics. So I go back to this question is, should I study quality or reliability in the statistics world? It says, well, both, and you need to understand failures and failure mechanisms, and you need to understand business and what's important, not important, and what's going to add value so you can choose what to work on, and on and on and on. Statistics is a wonderful tool that we have available. And over time, we've gotten more and more elaborate tools to use. And it might be a subject for yet another podcast, is that even with the advent of computers, we seem to have really slowed down with our ability to use them to really understand what's going on. I think in our last episode, we talked about that very few software packages deal with informative right censoring or left censoring very well, if at all. And it's a shame, because we should be thinking about what we're doing, whatever kind of statistics we're doing, is one, why are we doing this? Does this matter? Is it worth pursuing this analysis? And then two, to what end? What action are we going to take once we get this curve fit? Or we do this, we get this process that says it's not stable. Well, part of being an engineer, quality or reliability or any field, is you got to make a difference. The statistics gives us a window into what's going on like no other. Yet if we don't use that information to make a difference, it's really hard to justify having a computer to do the stats for you.
Yeah, no, and we have to, I guess I'll make a statement that'll probably get me in trouble, but we have to not be software jockeys, even though the younger generation, and I'm singling out the younger generation here, but really gravitates to flashy computer programs that I plug my data into, and it gives me a beautiful graph. Yeah. That beautiful graph has got to be right because it's beautiful.
Yeah.
And I think what you're saying is, no, it's not beautiful. We really have to look at and understand what the data is showing us, what the graph is showing us, and does that make sense? Because the computer algorithms, which have been around, the
some for a century, yeah.
Probably two. centuries at least, and then the maximum likelihood at least a century since Fisher wrote his paper. And you plug in the data in, it's going to give you an answer. It's a big calculator, but if you've put the wrong numbers into the calculator, you're going to get the wrong numbers out.
Yeah.
And we need to understand that. So I think I agree with you. Hopefully, I haven't made anybody furious, but if we just can't be software jockeys. We really need to understand the concepts.
Yeah. No. So all you software jockeys out there that trust their computer or calculator or slide rule or abacus or whatever you're using, let us know, where did we miss this? Or if you agree with us, that's even cooler. Send over your thoughts and comments. But either way, if you have a question about quality or reliability or how they fit together, or with Philip, I enjoyed talking about statistics. He does have a big library of stats books. It's pretty cool. So we could tap into that if we ask some good questions. But do so. Head over to accendoreliability.com/go/SOR. And Philip and I and the other hosts of the show are available through LinkedIn, and where this question came from, and our about pages. You can directly contact us through that. So plenty of ways for you to, ask a question and make us think a little bit and see how we can address that question and maybe expand it out into an interesting conversation. But so we'll look forward to some more of those. And by the way, Philip, this is episode in our tally sheet here, 988. So we're getting close to our 1,000th episode. So I'm really, I think we actually have a date for it now. It's supposed to publish sometime in September, I think.
Fantastic. Looking forward to that.
Yeah.
And, to our listeners, if you disagree, throw your virtual rocks gently in the form of a question, and we'll talk about it on a future episode. Fred?
Yeah, perfect. Thanks, Philip. We'll talk to you soon.
Bye now.
Yeah, take care. Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.